So, hi everyone at home. Welcome back to Wednesday evenings at Cambridge University Astronomy. Unfortunately, we have yet another cloudy evening for you. So there's going to be no stargazing, but that will be more than made up for by our very excellent speaker. I'm here with Jess Rigley, who is a final year PhD student here at the IOA, who is studying, what you can see the talk title, Habitable Zone Dust. And so today she's going to tell us all about this habitable zone dust and the search for other Earths, which I'm very excited about. So over to you, Jess.
So hi. So I'm going to talk about the topic of my PhD, which is this dust that we see in the habitable zones of other stars and why it matters when we look for Earth-like planets. Sorry. So I just want to start off by talking about our solar system. So if we think about what we have in the solar system, of course, the first thing we have is the sun. So the sun is the center of our solar system and everything else orbits around the sun. And then we have us on Earth. So Earth orbits the sun, and as astronomers, we use this distance as a unit. So the distance from the Earth to the sun is called 1 astronomical unit, or 1 AU for short. And we use this to measure distances in planetary systems. In the inner solar system, we also have the other terrestrial planets, or rocky planets. So we have Mercury, Venus, Earth, and Mars. As these are all quite small rocky planets close to the sun. And then further out, we have the giant planets. So we have Jupiter and Saturn, which are the gas giants. And then we have Uranus and Neptune, which are ice giants. So as we get further away from the sun, things receive less light, so things are colder. And so that means we go from having rocky planets closer to the sun to icy planets further away from the sun. And so this is the sun and all of the planets in our solar system. But there's actually more to the solar system than this, which you might not know. So we also have the asteroid belt, and this sits in between the orbits of Mars and Jupiter. So I should mention this diagram is not to scale, because if it was, nothing would fit on this screen as it would all be so spread out. But the asteroid belt is actually 3 times further away from the sun than Earth, or 3 astronomical units from the sun. And in this asteroid belt, we have lots of asteroids, which are essentially giant rocks. And we think they were just kind of leftover material from what the planets were made out of. So when the planets were forming, these rocks, for some reason, didn't form planets and just got left over. And then even further out, we also have the Kuiper belt. So this Kuiper belt is really far from the sun. It's around 30 to 50 times further from the sun than we are. So in the Kuiper belt, everything is really, really cold. So it's kind of like the asteroid belt, but instead of having giant rocks, these bodies are also quite icy. So they're big balls of rock and ice. And they have lots of different ices like water ice, methane, ammonia. And we also have some dwarf planets in the Kuiper belt. So for example, Pluto is not a planet. It's a dwarf planet because it orbits in the Kuiper belt and doesn't clear out its own orbit. And then every now and again, one of these giant Kuiper belt objects gets thrown into the sun. And this happens because of the gravity of these giant planets, because these giant planets are so massive that their gravity can pull things out of the Kuiper belt and throw it to the sun. And when this happens, this is called a comet. So I just want to talk briefly about what the habitable zone actually is. So the habitable zone is defined as the distances from a star where a planet can orbit and have liquid water on the surface of the planet. So if you go back to this idea of closer to the star, things are much hotter as things receive more light, whereas further away from the star, things don't receive as much light, so things are much colder. And so this is sometimes called the Goldilocks zone, because the idea is it's not too hot, it's not too cold, it's just right. So for example, in our solar system, we're quite lucky on Earth in that we sit smack bang in the middle of our habitable zone, which means we have the perfect conditions to have liquid water. Whereas, for example, Venus is just on the inner edge of the habitable zone, and Mars is just on the outer boundary of our habitable zone. And I should mention that even though it's called the habitable zone, just because a planet lies in the habitable zone doesn't necessarily mean it has life or could have life. We just use this as a metric to try and say, where could we have planets with life? Because we think that for life as we know it, we need liquid water. So even if we do find a planet in the habitable zone, it doesn't mean we found life. It just means that's more interesting to look at that planet to see if there is life there. So if we come back to the asteroid belt, so this is the belt that sits in between Mars and Jupiter, about 3 times further from the sun than we are. And there's about 1 million asteroids in this belt. And these are giant rocks, which have a whole range of sizes. So they can go from 1 kilometer in size to the largest asteroids, which are 500 kilometers in size. And this is a picture of an artist's concept of what we think it looks like in the asteroid belt. So we have all these asteroids orbiting the sun, and they're constantly smashing into each other. And when they collide together, they then break up into smaller fragments. And then those smaller fragments break up into even smaller fragments, and so on, until they produce things which are really, really small, called dust. So when I talk about dust in the astronomical sense, what I'm essentially saying is teeny tiny microscopic particles of rock. And so these can have a whole range of sizes too. This range of sizes for dust is from 1 micron to 1 centimeter in size. And so you're probably familiar with what a centimeter is. So that's something relatively small, but we can see it with the human eye. It's almost like a small pebble. But a micron is so small that we can't see it with the human eye. So for example, a human hair is 70 microns thick. So it's a 70th of a human hair. So these are really teeny tiny particles, some of them. And the reason this dust is interesting is that when we look at other stars, we can't see the asteroids and comets because in the grand scheme of things, they're relatively small and they don't emit their own light. But what we can see is this dust, which is produced by asteroids and comets. And that's because these dust grains are so small that if we look with certain wavelengths of light called infrared, the dust grains are actually comparable to the wavelength of light. And that means that we can then see emission from the dust grains and detect dust around other stars. And if we can detect dust around other stars, that means that there's asteroids and comets there producing the dust. And so we can then learn about the asteroids and comets around other stars too. And so we also have these comets. And so remember, these come from the Kuiper belt. So they start off really, really far from the sun, and then the gravity of the giant planets throws them in towards the sun. And they get put on very eccentric orbits. And what that means is that their orbits look a bit like this. So rather than being a circle around the sun, they're this elongated elliptical shape. So they start off really far away from the sun, like here, and then they get really, really close to the sun. And then they go really, really far away again, and then they get really close again. And so what this means is that the comets are going from being really, really cold when they're far away from the sun to being really, really hot when they're close to the sun, and then they get really cold again and really hot again. And because they have lots of ices, when they get close to the sun, they heat up and the ices start to sublimate. And what this means is that so when we have a solid, if a solid melts, it goes straight from being a solid to a liquid. But if a solid sublimates, it goes straight from being a solid to a gas. So these ices in the comet essentially just vaporize when it gets close to the sun. And this means that the comet starts spewing out lots and lots of dust and gas. And so these are a couple of pictures of comets doing just that and spewing out lots of material. So comets essentially have 3 different parts. So first of all, we have the nucleus. So this is the object that started off in the Kuiper belt, which is a giant ball of rock, dust, and ice. So scientists sometimes call comets dirty snowballs because they're just this big bundle of rock and ice. And these are similar to the asteroids in size. So they're also kilometers in size, going from 1 kilometer to hundreds of kilometers. So they're very big rocks, but they also have lots of ice. And then as they get close to the sun and heat up, they spew out all this material. And we see this in 2 ways. So the first way is the coma. So for example, this is a picture of comet Ison. And so you can see the nucleus of the comet here. And then it also has this coma around the nucleus, which is all the gas and dust coming off the comet. And then we have the second picture here, which shows really nicely the tail of the comet. So some of this dust and gas gets blown away from the sun and streaks out behind the comet. So this is comet Hale-Bopp, which is a comet from the 90s. And we can see it actually has 2 different tails. So this first tail at the bottom is the dust that's being released from the comet. And this second tail here, which is blue, is gas ions. So this is the gas being released from the comet, which has been ionized by the sun's light. But there's another way that comets can produce mass. So sometimes we actually see they just spontaneously break up. For example, this is a picture of a comet, of a fragment of a very famous split comet. So this is one of the largest fragments of comet 73P. And so you can see that this fragment is again breaking up into even smaller bits. So these arrows are pointing to smaller fragments breaking off the main fragment. So it's now breaking up into 1, 2, 3, 4, 5, 6, 7 other fragments. And we're not really sure why this happens. We have a few ideas. So one possibility is rotational spin-up. So as a comet's hurtling through space, it's going to be spinning around. And let's say it has lots of ice on one side, which is then sublimating. And so it's spewing out lots of material from one side. This can then cause the comet to spin faster and faster and faster as it exerts a torque. And so if the comet spins so fast, it could just spontaneously break up. Another reason is thermal stress. And this is because if we think about the orbit of the comet, it starts off really far away from the sun, and then it gets really close. So it goes from being really hot to really cold to really hot again. And so this means that it's experiencing a large range of temperatures, which could then weaken the material of the comet. And then the third reason is the sublimation of ices. So if there's ice trapped underneath the surface of the comet, and those ices then sublimate, then you have loads of gas trapped underneath the surface. And so this could cause lots of material to just break off. So if we go back to our picture of the solar system, we have the sun, we have the planets, and we have the asteroid and Kuiper belts. But we also have a lot of dust. And we do have dust all throughout the solar system, all the way out to the Kuiper belt. So the Kuiper objects will also be colliding together and producing dust, just like in the asteroid belt, but it's much less. And so that's why I've drawn it here as mostly concentrated inside the orbit of Jupiter. And we call this dust zodiacal dust. And this is essentially just interplanetary dust, which is just orbiting out in between the planets. And we think it's come from a combination of these asteroids and these comets, although we think that the main source is this spontaneous breakup of comets. And so you might have heard of the zodiacal light. So you can actually see this dust as the zodiacal light. So this is a picture from ESO's La Silla Observatory in Chile. And we can see here this really beautiful white triangular glow above the horizon. And that is the zodiacal light. And it's essentially just the sunlight reflecting off these zodiacal dust grains, which are orbiting out near Earth. And then we can see it just after the sun sets. So that's our zodiacal cloud. But what about other stars? So we know that other stars also have this zodiacal dust, and we call it exozodiacal dust, where the exo bit just means it's around a different star. So it's another planetary system separate from our solar system. And we know this dust lies in the habitable zones of those stars based on its temperature. So this is just a picture of how we actually detect that dust. So the idea is that this shows how much light we see when we look at a star with different wavelengths. So across the bottom here, we're changing the wavelength we look at, and then we're saying how much light do we see from the star. And if we know the temperature of a star, then we can say, well, we know how much light we expect to see. And so that's what this black line is showing. This is saying we know how much light we expect to see from the star, and it should look like this. But then sometimes at certain wavelengths, we see more light than we expect. And this extra light is coming from dust that's orbiting the star. And the wavelength we look at determines where that dust is. So if dust is really close to the star, it's going to be really hot. And so we'll see it when we look at really short wavelengths. Whereas if dust is further away and colder, we'll see it when we look at longer wavelengths. So for this warm habitable zone dust that I'm talking about, we need to look in what's called the mid-infrared wavelengths. So we look at wavelengths of around 10 microns. And this allows us to see dust that's at a similar distance from the star as we are from our sun. So this is why this says 1 to 10 AU. So why should we even care about this dust anyway? There's essentially two different reasons. The first one is that it's really hard to see what's going on close to a star, but if we know what's going on with the dust close to the star, that can tell us something about what planets are there and what those planets are doing. So it's essentially another way to learn about what's going on in other planetary systems. But the main reason is that it gets in the way when we try to look for Earth-like planets. So for example, this shows a simulation of what will happen when we try to look for other Earths. So in this simulation, we essentially have an Earth-like planet orbiting a star at the same distance as we are from our sun, so 1 AU. And if we look at the right-hand panels, these are what we detect. And we're changing the levels of exosodiacal dust, and we're measuring this in units of zodies. So 1 zodi is the amount of dust we have in our zodiacal cloud. So if we start off with our zodiacal cloud and we try and look for an Earth-like planet, you can see we get this red dot, which is essentially a detection of the planet. So we can see the planets there really clearly. So our solar system isn't too dusty, so it would be quite easy to see the Earth-like planet. But if we increase it to 5 or even 10 times our zodiacal cloud, so if we look here, you can still see the planet there as a red blob, but we can also see a lot of dust. So while we can still see the planet, it's really not as obvious now, and it's much harder to see that it's there. And then if we go over here to where we have 20 zodies, or 20 times our zodiacal cloud, where the planet is, you can't actually really see it anymore. And it's kind of been eclipsed by the dust. And now, instead, we're seeing this other red blob here, and this is not the planet. This is a clump of dust, which is essentially trailing the planet on its orbit. And so we're not detecting the planet, and instead we're detecting this clump of dust, which looks like a planet, but isn't. And then as we get to 50 or 100 times our zodiacal cloud, the planet is completely eclipsed by dust, and we cannot detect it whatsoever. And so this means that when we're designing missions to look for Earth-like planets, we really need to understand what's going on with this dust, because it's going to get in the way. So we want to know how often we expect to see it, and we also want to know where it comes from, so we can take into account the dust and get rid of it so we can see the planets. So to detect this dust, again, because it's so close to the star, it's also quite hard to see this dust in the habitable zone. And so we have to use a special technique called interferometry. So this is a telescope we use to look for the dust. It's called the Large Binocular Telescope Interferometer, or LBTI. And this is a telescope in Arizona. And you can see it's actually got 2 telescopes. So it has 2 8-meter telescopes, and both telescopes look at the star at the same time. And so this is something called nulling interferometry. And the idea is you look at the star with 2 telescopes, and then you combine the light from the 2 telescopes in a special way called destructive interference. And this means that we can actually cancel out the light from the star, and then we can resolve dust that's really, really close to the star. And so we use this telescope to look for exozodiacal dust around lots of other nearby stars. And this is what we found about how common it was. So this shows the detection rates for different categories of stars. The main result is this purple bar here. So out of all the stars we looked at 38 nearby stars for warm exozodiacal dust, and we detected it around 10 of those stars. So that means we're seeing this dust around roughly 1 in 4 stars. Although I should note that with this, even with this state-of-the-art technique, we can only detect levels of exozodiacal dust that are around 30 times more than our zodiacal cloud. So all of these stars are much, much dustier than our solar system. And that means that there's probably lots of these stars that have levels of dust comparable to our solar system, and we just can't detect it yet with our current techniques. So even at these really high levels of dust, we're still seeing it around 1 in 4 stars, which means it's actually pretty common. And the other key result from our survey was that we see this a lot more often around stars which have cold dust. So for example, this red bar here shows that 7 out of the 9 stars with cold dust also had warm exosodies. And this cold dust tells us that we have a Kuiper belt around the star. So what this is saying is that if a star has a Kuiper belt, it's much more likely to also have this warm dust in the habitable zone. And that's important because maybe the two could be linked somehow. And then the other thing to note from this is that we see this around stars of all ages. For example, our sun is quite old. It's 4.5 billion years old. And it might be, if we only saw this around young stars, that might tell us something about where the dust is coming from, but it turns out we just see it around stars of all ages. So we don't really know what's going on. So now it comes to the question of where is this dust actually coming from? I mean, you might say, well, could we have an asteroid belt that's in the or close to the habitable zone? Because we know that asteroids would collide together and produce lots of dust. So maybe we're just seeing dust from asteroids colliding. But the problem with this is that if we have an asteroid belt undergoing lots of collisions, all the asteroids are going to break up. And so the asteroid belt wouldn't survive for long enough to produce enough dust to explain what we're seeing. So we know it's not asteroid belts in most cases, unless the star is very young. But given we have this link between a cold Kuiper belt and this warm dust, it's possible that maybe the dust starts further away from the star and somehow gets transported inwards. So for example, this image here compares two stars. So on the right, we have a top-down view of our solar system. So we have the sun at the center, we have the asteroid belt here and the giant planets, and then we have our Kuiper belt, which orbits outside all the giant planets. And this has been scaled up to match this other star. So this shows the solar system actually to scale compared to Vega. So this is our Kuiper belt, which is around 30 to 50 times further away from the sun than we are. And then we have this other star, Vega. So this is one of the stars we looked at, and we know it has lots of this warm dust. So this star has around 30 times more zodiacal dust than our solar system. And we also know it has a really massive Kuiper belt analog. The only difference is that this Kuiper belt is around 100 times further from the sun than we are. So this is about 3 times further from its star than our Kuiper belt is from our sun. And so we want to know, well, maybe the dust is somehow being produced in this outer belt and then being transported in towards the star. And so one possible way that this could happen is something called PR drag, or Poynting-Robertson drag. And the idea is that these dust grains are so tiny, remember they're microscopic, that when sunlight hits a dust grain, the dust grain is so tiny that light actually exerts a force on the dust grain. And this is something that's called radiation pressure. So if a dust grain is orbiting a star, it doesn't just stay where it is. The sunlight actually affects the motion of the dust grain. And part of this radiation pressure is a drag force called PR drag. And so if we have dust produced in this outer belt, PR drag causes it to slowly spiral in towards the star on really long timescales, but it will slowly reach the habitable zone of the star. And so maybe that's what's going on. And the dust is being produced out here by collisions between these Kuiper belt objects and then slowly drifting towards the star. And so this is what I tried to model in the first part of my PhD. And there's a lot going on in this plot. But the key points are that this is showing levels of exozodiacal dust versus how far away the outer belt would be from the star. So remember, our Kuiper belt is around 30 AU from the star, from our sun. So our Kuiper belt would be around here. So most of these belts we're looking at are further away than our Kuiper belt. And all these X's are the stars that we looked at with our survey when we used the Large Binocular Telescope Interferometer. So this shows how much exozodiacal dust we saw around all these different stars versus how far their outer belts are from the star. And then these various lines are just showing predictions from my model of how much dust could be dragged towards the habitable zone for different parameters. But the key thing here is that the levels of dust predicted by my model generally lie below these levels that we're detecting around other stars. So even if I had a really, really massive outer belt, PR drag could not explain these observations. because it just wouldn't drag enough dust into the habitable zone. And so that means, while yes, this can produce some exozodiacal dust, in most cases, it just cannot produce enough. And so that means something else must be going on to explain how this dust gets here. And so the other alternative explanation is exocomets. So in our solar system, we now think that our zodiacal cloud is mostly produced by comets just spontaneously breaking up. So maybe this could also explain this exozodiacal dust. And so this is a diagram of what that would look like. So if we have an outer belt similar to our Kuiper belt, and we have lots of comets far away from the star, then if we have these planets, which are shown in orange, the gravity of these planets can then pull comets out of the belt and scatter them in towards the star. And then as the comets start to get close to the star, they can start to just spontaneously break up and produce lots of dust. And then this dust could supply an exozodiacal cloud. And so this could be what's going on. And this is what I now try to model as a potential source of exozodiacal dust. And then this is just a couple of other possibilities. So two other possibilities for what's going on. The first one is giant impacts. So you might have heard the story of how we think the moon formed. So we think that when the solar system was much younger, a giant protoplanet, so basically a giant body that was going to become a planet about the size of Mars, just smashed into Earth. And we had this giant collision. And part of that is that the moon broke off. So the moon was a fragment from a giant collision between Earth and some other Mars-sized body. And this is called a giant impact. And this is a picture of what we think a giant impact would look like. So if we have two giant planetary-sized bodies colliding together, then of course they're going to produce lots of fragments and lots of dust, as shown here. And so if there was a giant impact around another star, we think we could detect that as exozodiacal dust. For example, this is a simulation of what we think we would see if we looked around a star when it was undergoing a giant impact. So this is what we would see with the James Webb Telescope, which is hopefully going up in a couple months' time. And so you can see that we would actually detect this giant impact. And we think that these are actually quite common when stars are particularly young and just forming their rocky planets. So this could especially be a good explanation around younger stars, which are still forming planets. And then another possibility is something called dynamical instabilities. And so we think that when the solar system was much younger, we had something called the late heavy bombardment. And essentially what happened was lots of comets were thrown in from the Kuiper belt towards the sun, all at the same time. And so if we had lots of comets thrown in towards the star at the same time, which then all sublimate and produce lots of dust, then that could also potentially be a good source of exozodiacal dust. But the problem with this one is that we think that this just doesn't happen often enough to explain all these detections we're seeing. So I just want to finish by briefly mentioning a couple of mission concepts for finding Earth-like planets. So these are very much still in the planning stages. At the moment, we cannot detect Earth-like planets with our current telescopes. And it's actually a really challenging thing to do for two reasons. The first one is we want to look for planets in the habitable zone, which means we're looking really close to the star. And obviously, as stars are so far away, it's really hard to resolve such small distances on the sky. And so for that reason, we need very big telescopes. But the second reason is the contrast between the planet and the star. So if we think about a planet, it's not emitting its own light. The only light we can see from a planet is starlight, which is reflected off the planet. And so that means there's actually a really high contrast between the planet and the star. So the planet will be 10 billion times fainter than the star. So it's 10,000 million times fainter. And that's actually really difficult to see. If we look at a star and then we're trying to see something that's 10 billion times fainter and really close, that's actually quite technically challenging. And so we have these two mission concepts for NASA, which would hopefully one of them might go up in the 2030s, although we don't really know yet. And so this first one is LUVOIR, So this is the Large UV Optical Infrared Surveyor. So both of these would be space telescopes because we need to go to space for this. And this one would either have an 8-meter or a 15-meter telescope. And then it would use something called a coronagraph to block out the light from the star so that it could see planets really close to the star. And so a coronagraph is basically, if we're looking at a star and then we put something over to cover the middle of the telescope to like block out the starlight, and that helps us see things that are really, really close to the star. And then this second mission is called HabEx. So this is the Habitable Exoplanet Observatory. And this one's a much smaller telescope. So this is only a 4-meter telescope, but this one's actually 2 spacecraft. So as well as a 4-meter telescope, we also have this star shade. So this star shade is 52 meters across. And essentially they have to communicate with each other so that they line up. And so the telescope points at the star, and then the star shade aligns itself so that it covers just the star. And then you can block out the light from the star and see things really close to the star, hopefully. And so both these missions would try to image Earth-like planets, and they would also try to look at the atmospheres of those planets, because the first goal is to find Earth-like planets, and the second goal is to find, is there life there? And so to do that, one way is to look for what's in the atmospheres. So we look for something called biosignatures, which is essentially different chemicals which could signify that life is there. So for example, we might look for water or ozone or carbon dioxide or methane. And these kind of chemicals could then, if we detect them, could say maybe there's life on those planets. And then one other mission, which is even more preliminary, is called LIFE. And so this is the Large Interferometer for Exoplanets. And so this would do something similar to the Large Binocular Telescope Interferometer that I mentioned earlier, except this would do it in space. So again, this would combine 4 telescopes, all flying in formation. So they have to communicate together where they are in space, and they all look at the star at the same time. And then you can kind of combine the light from the different telescopes together to then find Earth-like planets. Thank you. Any questions?
Wonderful. Thank you so much, Jess. That was really fascinating. I love there's a unit called the Zodi. That's really satisfying. So for anyone watching, you want to ask our speaker a question, just pop them down here in the YouTube chat. Someone actually tweeted a question at us. They want to know, you talked a lot about the habitable zone. If Earth is in the habitable zone, in the Goldilocks zone, why do people spend time looking for life on Mars?
Well, I mean, Mars is technically on the outer edge of the habitable zone, so I think it is possible there could be liquid water there. But I mean, we don't necessarily need water for there to be life there. I guess the point is Mars is, in the grand scheme of things, Mars is relatively close by, so it's more accessible. When we're looking around other stars, in our lifetimes, realistically, we're never going to get to those planets. So it would be very exciting if there was life on Mars. And I guess it is possible there could be. And there could be other forms of life, right? So it could be that there's life that's not quite as we know it. So maybe special kinds of bacteria or something like that.
Yeah, that's what I was going to mention, actually, because a lot of the habitable zone stuff is predicated on this idea of life as we know it, right? And we have, kind of weird things down here on Earth that live in extreme conditions. I don't know, can you talk about that for a moment?
Yeah, like, for example, well, I mean, I don't know if people know about Venus. So there was a big thing with Venus, was it last year, where we detected phosphine, which again is one of these potential biosignatures in the atmosphere of Venus. Although, I mean, I think it's still a bit controversial if it's actually a robust detection, but we potentially detected a biosignature in Venus. But Venus actually, in its atmosphere, it has like sulfuric acid clouds, basically. So it was like, well, how could anything survive in that atmosphere? And so then they came up with this whole mechanism of how you could have special bacteria which live in these like bubbles, and then I don't know, the bubbles sink or something. But we know, like, for example, on Earth, we do have a lot of bacteria that live in like really extreme environments, like volcanic vents or like you might have heard of something called a tardigrade, which is these tiny, like single cell, well, are they single cell, like really small microscopic organisms, and they can take any beating. Like you could throw a tardigrade into space and it would survive. They just survive absolutely anything, and they're amazing.
Yeah, tardigrades are amazing. Yeah, they can survive, vacuum of space and minus 200 degrees and nuclear explosions, probably. They're kind of amazing. Someone said this might be the last question. Yes, remember, it's questions for our speaker in the YouTube chat. Someone asked a question about Mars. Do you think that going to Mars is the future of the human race? How do you feel about this idea of kind of terrestrializing other planets?
Yeah, I don't know. Well, I guess for me, like, I think it's an exciting thing to try and colonize other planets, but I think we also, we have to realize that it's really important to look after the planet we do have already. And I do wish people would prioritize that more. We can't just escape to other planets. But I guess it is exciting to try and colonize Mars. Yeah.
Yeah, I think that's really good. I mean, definitely exciting, but yeah, no substitute for saving the planet we're on. I think you're absolutely right.
Yeah, we can't just run away from our problems.
Amazing. Well, Jess, thank you so much. That was absolutely fascinating. It was a really, really nice topic to hear about and think about. And thank you for everyone at home listening. I hope you have enjoyed tonight's talk. Tune in again next week. So we do these talks every Wednesday evening through the winter. So 7:15 next Wednesday for another wonderful talk. Wonderful. See you guys next week.